All right, diving right in today, time travel.
Yeah.
I mean, it's such a classic. So, you sent me this really interesting material
Hmm.
that basically looks at, is time travel possible? And we're not talking, science fiction here. We're going full on, science.
Into the real physics of it.
Yeah, the real deal. What's the reality of the science of time travel? So basically, over the course of this, deep dive, we're going to be going through a bunch of stuff. We'll talk about the nature of time itself. We'll get into Einstein, obviously, relativity, wormholes, the paradoxes that always come up, quantum mechanics. What are the limitations? I mean, can we actually do this? And then, even some of the philosophical stuff that comes up. So, are you ready?
Yeah. Let's go.
Okay, let's get into it. Now, I always like to start with the basics,
Sure.
just to make sure we're all on the same page. So, when we talk about time, what actually are we talking about? I mean, we experience it every day, but what is it, fundamentally in physics?
Well,
Well, it's really fascinating. We kind of think of time as this separate thing, right? But physicists, they think about it as the fourth dimension, part of this thing called space-time.
oh, okay.
So it's not just like you've got length, width, and height. You also have this time component, and all of these things together make up this kind of arena where everything exists and everything happens. So it's like the stage, and the stage also has this temporal dimension to it. That's space-time.
So space-time is like this four-dimensional, world that we live in. It's not just space, it's space and time all woven together.
Exactly.
Okay. So this whole understanding of time, it really kind of got revolutionized, when Einstein came along, right?
Right.
With his theory of relativity. It kind of blew everything wide open.
Absolutely. I mean, both of his theories of relativity, special and general relativity, they completely transformed how we think about space and time.
Hmm.
And, one of the biggest, kind of revelations from those theories is that time, it's not this absolute thing that's ticking away at the same rate for everyone everywhere. It's relative.
Oh, okay.
So what that means is that the rate at which time passes for you, that depends on things like how fast you're moving or the strength of the gravitational field that you're in. It's all relative to the observer.
So it's not like there's one universal clock for the whole universe.
Right. Exactly. It's a personal experience of time.
So I move faster, time slows down for me. Am I getting that right?
Yeah, that's the gist of it. And
Okay.
that's where the concept of time dilation comes in.
Time dilation.
Yeah. So the faster you're moving, the slower time is going to pass for you relative to someone who's stationary. Now, it sounds like pure science fiction, I know,
It does.
but it's been experimentally confirmed.
Really?
Yeah, they've actually, one of the experiments mentioned in the material you sent is they use atomic clocks, which are super, super accurate.
Okay.
And they take these clocks, put them on like high-speed aircraft, fly them around, and then they compare them to identical clocks that have been left on the ground. And what they find is that the clocks that were flying, they actually show a tiny bit less time has passed.
Wow.
It's a tiny difference, but it's measurable. And it's direct confirmation of this idea of time dilation because of relative velocity.
So it's like the faster you go, the more you're kind of stretching time out behind you.
In a way, yeah.
Yeah.
It's like your own personal time is slowing down.
Okay. And then gravity also plays a role in this, right? Like the material also talked about how gravity warps time. How does that work?
Right. So far we've been talking about special relativity.
Mhm.
Now we bring in general relativity, which
Mm.
is Einstein's theory of gravity.
Mm-hmm.
And basically what general relativity says is that gravity, it's not just a force, it's actually a curvature in space-time. And that curvature is caused by mass and energy. So massive objects, they actually warp the fabric of space-time around them.
Mm.
And this warping, it affects the flow of time. So the stronger the gravitational field, the more time slows down.
So if I was hanging out near a black hole, which has super strong gravity, time would move slower for me than for someone back on Earth.
Exactly. Your watch would literally tick slower.
That's wild. So theoretically, if we could harness this, if we could go super fast or hang out near a black hole, we could kind of travel into the future, right? I mean, at least relative to everyone else.
In a sense, yes. You would age slower compared to everyone else.
But what about going the other way? What about going back in time?
Right. So that's where the concept of wormholes comes in, which is, another very popular idea in science
You
fiction.
have wormholes. They're like shortcuts, right?
Yeah. Think of it this way. Imagine space-time as like a fabric, and this fabric can be bent and folded, right?
Yeah, okay.
So a wormhole is theoretically a tunnel or a bridge that connects two very distant points in this folded fabric.
Like a shortcut
Exactly.
through space-time. Okay.
And these connections, they could be across vast cosmic distances, or they could even potentially connect two different points in time.
So you could like step into a wormhole and pop out in like the Jurassic period?
Well, theoretically.
Yeah.
But again, this is all very theoretical.
Right.
There's no observational evidence that wormholes actually exist. And even if they do, there are huge challenges.
Like what?
Well, for one thing, how do you keep them stable? Wormholes are thought to be very unstable. They might collapse instantly. And even if you could keep one open, how would you actually travel through it safely? These are all questions that, are way beyond our current science and technology.
Right. So wormholes, big maybe, but a very cool idea.
Yeah.
Now, time travel to the past, it also brings up a whole bunch of like paradoxes, doesn't it? Like you go back in time, you change something, and then what?
Exactly. And the most famous of these is the grandfather paradox.
Right, the grandfather paradox. Like, I go back in time and I accidentally prevent my grandparents from meeting.
Right.
So then I'm never born.
So then you couldn't have traveled back in time in the first place. It creates this big logical contradiction.
Yeah, a real mind bender. So how do we get around that? I mean, does physics have an answer?
Well, there are some proposed resolutions, and one of the most interesting ones is Novikov's self-consistency principle.
Novikov's self-consistency principle.
Okay, so this principle basically says that if you were to travel back in time, any action you take, it would have to be consistent with the history that you already know.
Okay.
So you wouldn't be able to change the past in any way that would create a paradox. Your actions would have to be part of the fabric of history, making it self-consistent. So even if you try to go back and stop your grandparents from meeting, something would always happen to prevent that from actually changing the timeline. Right. You might get sidetracked, they might bump into each other anyway, something.
So, like, the universe would somehow protect itself from paradoxes.
That's the idea. It's like there's this built-in safeguard.
Okay. So maybe the past isn't as, changeable as we might think.
Right.
Now, the material also mentioned quantum mechanics. Like, does that have anything to say about time travel?
It does. It's a very different way of looking at things, but quantum mechanics offers some really interesting perspectives on time travel. Some interpretations suggest that at the quantum level, particles might be doing things that could be interpreted as traveling backwards in time, although it's very different from the kind of, large-scale time travel we see in movies.
So, like, what are we talking about here? Like, particles zipping back and forth in time?
Well, one example is the concept of antimatter. Mathematically, you can actually think of antimatter as ordinary matter that's moving backwards in time. And then there are things called virtual particles, which kind of pop in and out of existence. And sometimes they seem to violate our normal ideas about the direction of time. And then there are some really wild theories that try to connect quantum entanglement, that spooky action at a distance, to the possibility of creating connections through space-time, potentially even linking different points in time.
So even though we're not going to be building a time machine out of, like, subatomic particles anytime soon, there might be something about the fundamental nature of reality that, at the smallest scales, is way more fluid and interconnected when it comes to time.
Right. It might not be as straightforward as we think.
Okay, now, all of this is fascinating.
Yeah.
But we've got to come back down to earth a bit here. The material also talked about, the practical limitations, the challenges.
Right.
Are we ever actually going to be able to build a time machine, or is this all just, really cool theoretical physics?
Well, as exciting as the theories are, the reality is that the practical challenges are immense, especially when it comes to traveling back in time.
Like, what are we up against here?
Well, for one thing, remember we talked about time dilation. To travel at speeds that would allow for significant time dilation, you would need an unbelievable amount of energy, way more than we can currently produce or even imagine controlling.
Okay.
And then for wormholes, even if they exist, creating one and keeping it stable, that would probably require something called exotic matter, which is this hypothetical stuff with negative mass energy density. We've never even seen it, let alone figured out how to harness it.
So not just the physics, but the engineering challenges are, like, off the chart.
Exactly. We're talking about manipulating the fabric of space-time, and that's not something we're anywhere close to being able to do.
So no time travel vacations in the near future.
Not likely.
But research is still going on, right? I mean, scientists are still trying to understand all of this.
Absolutely.
Yeah.
I mean, even though we can't build a time machine right now, there's so much we still don't know about time and space-time.
Yeah.
And scientists all over the world, they're still actively researching, trying to understand the fundamental nature of time, gravity, quantum mechanics. And every new discovery, it could potentially open up new possibilities, new avenues to explore.
So we're still in the early days of understanding all of this.
Yeah, it's a journey of discovery.
Okay. Now let's shift gears a bit.
Okay.
Because time travel, it's not just about the science, it's also about the philosophical questions, the implications.
Right.
I mean, if we could actually change the past, what would that mean for, our understanding of cause and effect?
Yeah, it raises all sorts of questions about free will versus determinism. If the past is not fixed, if it can be changed, does that mean our choices in the present are already predetermined by what might happen in the future? Or does it mean that the past is constantly in flux, depending on the actions of potential time travelers? It really challenges our whole linear understanding of time,
And then there's the whole ethical dimension.
right? The ethics of time travel. If you could go back and change things, what kind of responsibility would you have?
Yeah.
I mean, would you just be an observer? Or could even the smallest action have huge unintended consequences?
Yeah. Ripple effects could be crazy.
Exactly. And then there's the potential for abuse, right? What if someone used time travel for their own selfish purposes?
It's like a Pandora's box of potential problems.
Yeah, it's a really fascinating area to think about.
Now, it's no surprise that all of this, this whole idea of time travel has been like super inspiring for storytellers. The material you sent had some great examples from pop culture.
Yeah, time travel is a classic theme in science fiction,
Yeah.
and it allows writers and filmmakers to explore these really complex ideas about time, causality, choice, consequence.
Okay.
Movies like Back to the Future, they often take a more like adventurous, sometimes humorous approach.
Yeah.
They play around with the paradoxes, the idea of changing the past for, personal gain.
I mean, who hasn't wished they could go back and change something, right?
Exactly. And then there are movies like Looper that get into the darker, more morally ambiguous sides of time travel.
Yeah.
The violence, the exploitation,
Ah.
the questions of destiny versus free will.
Okay.
And then there are movies like Primer, which they really delve into the complexities, the unintended consequences, the really mind-bending stuff.
And all of these movies, they're not just entertainment, they're actually grappling with the same questions that scientists and philosophers are asking about time travel.
Absolutely. It shows how deeply this idea resonates with us.
So looking ahead, what's next for, the research side of things? Are scientists going to keep digging into this, or are we kind of at a dead end?
Well, we might not have a working time machine anytime soon, but the research into the fundamental nature of time, that's definitely not stopping.
Okay.
Theoretical physicists are still hard at work, exploring things like quantum gravity, which is this attempt to unify our understanding of gravity with quantum mechanics.
Yeah.
And then there's string theory, other, advanced theoretical frameworks, and any breakthrough in these areas could completely change how we think about time and whether or not it can be manipulated.
So we might get some really big surprises down the line.
It's definitely possible. And then there's also the experimental side of things. As we make advances in fields like particle physics and cosmology, we're getting better at measuring fundamental constants, observing extreme cosmic phenomena. And those observations, they could give us clues, hints about how time really works.
So while we might not be punching in dates on our time travel devices just yet,
Right.
the journey to understand time, it's a really exciting one.
Absolutely. And it's one that's full of possibilities.
So for now, time travel will stay in the realm of, thought experiments in science fiction.
For now.
But I think it's safe to say that our fascination with time, it's not going away anytime soon.
No, and I think that's a good thing. Because this drive to understand time, it's pushing us to learn more about the universe, about ourselves, about the very nature of reality. And who knows, maybe someday, all of this research, it'll lead to something truly amazing, something that right now we can only dream of.
Absolutely.
Yeah, it's a journey worth taking, even if we don't know where it'll end up.
Well said. Thanks for joining me on this deep dive into the science of time travel. It's been a really fascinating conversation.
My pleasure. It's always great to talk about this stuff.
And for all of you listening out there, keep those questions coming. Keep exploring. Keep that curiosity alive, because that's what drives us forward. That's what leads to new discoveries. And until next time, keep diving deep.